The first talk is by Bertrand Eynard from the Institute of Theoretical Physics, and he will speak about topological recursion and quantum curves.
Okay, so first I would like to thank the organizers for inviting me to this conference, and it's good to be back in Geneva, where I spent a year and a half, a couple of years ago. So the topic of my talk will be about topological recursion and quantization. Well, yesterday we already had some thing about, Don Zagier presented something about the asymptotic expansion of Jones polynomials. And there is a conjecture, which appeared recently, is that all the terms in that asymptotic expansion are related to the topological recursion. I think it was first introduced by Digraph, Fuji, and Manabe. Well, this is a conjecture, this is not proved. Well, so I will show many examples of where topological recursion is related to quantization and to asymptotic expansions. So I will start by introduction by an example with intersection numbers. Well, let MGN be the moduli space of Riemann surfaces of genus G with n mark points. On MGN bar, it's compactification. We shall consider the cotangent bundle to the ith mark point and its Chern class. And the intersection numbers, by definition, are integrals of some powers of Chern classes over MGN bar. And this makes sense only if the sum of powers, only if this is a top form. So only the sum of degrees, d1 plus dn equals 3g minus 3 plus n. Otherwise, we define it to be 0. And the Witten's notation is that one, so tau d1, tau dn, index g, while the n is, can be read by just the number of tau factors, the n of MGN. So this is just the definition. And we shall define a generating function for those numbers, which is, so we have one. For the moment, ignore this exponential term, but just take the product of tau di, index g, multiplied by dzi over zi, 2di plus 2, there is a combinatory factor, sum of all possible di's, and that's called that WGN, so it's the generating function of intersection numbers. You can make it even, well, depend on even more parameters by introducing those extra terms. You see that if you take all the tk's equals 0, you just have that. Vice versa, if you had no zi's, basically if you take just n equals 1 or even n equals 0, you also have another generating function for intersection numbers. So somehow there is a redundancy between the tk's and the zi's, but well, let's keep both for the moment. And also in the zi's, it is a differential form. So it's an n form on CP1 to the n. Well, so this is the definition. It just encodes all the intersection numbers. And it satisfies a strange property, which is related to that curve. Well, here I call, well, the curve should really be, if you eliminate z in this, between those two functions, you get a relationship between y and x, which is, well, if there is only a finite number of tk's, it is algebraic, and we call it the spectral curve. And the theorem is the following, that those generating functions satisfy the following property. They satisfy the following recursion. Well, you don't need to really see all the terms in this recursion, but observe that WGN plus 1 is related to some WG minus 1 and plus, well, it should be an n plus 2 here, and some product of other W's with lower indices somehow. So this is a recursion which allows to compute all of them. So recursively, basically, it's a recursion on 2g minus 2 plus n. And it determines everything. Well, just observe one thing here. Y is an odd function, and I wrote y of z minus y of minus z, so which you can rewrite this way, 1 over 4y in that case, but I wrote it this way before because it will generalize to curves which have no involution. So this is the topological recursion. So this is a case where it can be proved that the generating function of intersection numbers do satisfy that, and this is in some way it just translates the so-called Virasoro conditions on the intersection numbers. So it's just, I mean, it comes from the Virasoro condition. Another way to do that is using Kontsevich. Kontsevich introduced some fat graphs, some ribbon graphs to encode intersection numbers, and just by the combinatorics of those ribbon graphs, you can also find this recursion. So it satisfies that recursion. Well, let me show you that this recursion, it may look complicated, but it's in fact extremely easy to use. Let's take an example. Let's compute W11 using that recursion. Well, so this is just the rewriting of a recursion. In the right-hand side, there is only that term. So this is just the rewriting of a recursion. Let's compute it. And W02 was defined to be dz prime or z minus z prime to the square. So it's one form which has a double pole on the diagonal and no other pole. Basically, it will always be that. W02 will always be the 1 form on the curve, which has a double pole on the diagonal and other pole. It's the fundamental second kind differential. It's the derivative of the head kernel. I mean, it has many names. Or the green function. So let's do the computation. So we have this. We substitute this W02 by that, so it just makes minus z square over 4z square. Okay, since we have to compute a residue at 0,
what is y?
Sorry?
What is y in this
y
case?
was written here.
No, but what is it here? I mean, you have many fewer variables now.
Sorry?
What is y in this case? You have just one variable.
It's this function.
But still with all the tks.
Excuse me?
Uh-huh.
Yes, it involves all the tks.
No,
Yeah.
it was written choose tk equals 0. You've specialized a lot.
Okay, I will specialize to the tk equals 0 later.
Okay, so for the moment it's the fourth.
Well, it doesn't really matter. Let's do the computation with all the tks, and then we can specialize to tk equals 0. So we have this computation to do. So we do the Taylor expansion of all the terms. So this term, we put the z0 square in front, and it's 1 minus z square over z0 square. The y was z minus t1 over 3z cubed, so we put 1 z here, and 1 minus t1 over 3z square. Okay, so raise it to 1. Take the Taylor expansion of the inverse, so it's 1 plus z square over z0 square, 1 plus, okay? And you read the residue at 0 very easily. It's a residue of a triple pole, so it's basically this term plus that term. So this is what you get. You see it's a 3-line computation. It's extremely easy to use. So this recursion, it may look complicated, but in fact it's extremely easy. And you can just implement it on Mathematica. I have a Mathematica program to run it systematically, and it's extremely easy to use, and that's what you get. Let's see what it means about intersection numbers. So you have to identify with this expression for intersection numbers. Well, first I have to say what this exponential means. Well, this exponential means that you should Taylor expand the exponential. So the exponential is something like that: 1 plus t1 t2 tau 2 plus t2 tau 3 plus t1 square tau 2 square plus blah blah blah. So it's just the Taylor expansion of the exponential. Remember that all those intersection numbers are vanishing if the degree condition is not satisfied. So using the degree condition, so the degree condition is that 3g minus 3 plus the total number of the tau terms should be equal to the sum of the degrees. So for instance here the degree is 2, here it's 3, here it's 4, and so on. So in fact, the only terms which survive the degree condition are tau 1, 1 and tau 2, tau 0, 1. And so basically, this expression was equal to that. Now you can identify with this one, and you read that tau 1, 1 equals 1 over 24, and tau 2, tau 0 equals 1 over 24, which is something well known, in fact, in intersection theory. So we just recover some well-known results, but just using this topological recursion this way. So I just wanted to say that topological recursion is very easy to use. It's just computing Taylor expansions and picking residues. So then, now, indeed, let me consider the tk is equal 0. Now, okay. Let me define the following object. So psi, equals this sum. So it's a formal, basically it's the exponential of a formal power series in a formal parameter which I call h bar, which was basically what Don Zagier Vierovey called 1 over n, but let me call it h bar here. So it's a formal series in h bar, and it's the sum over g on n of h bar to the 2g minus 2 plus n over n factorial, and the integral of wgn in all variables from infinity to the same z. To the same z, and z is related to this x by x equals z squared. So it's just, so it's a definition. Let's see what we can do about that. With that, so let's compute the first orders. So when we replace, so W01 was y dx. So W01 was the form y dx. Maybe I should write it somewhere. W01 is y dx. So it's easy to, so here it just gives, so here in that case x was z squared and y was z. So it gives 2 over 3 z cubed, so which is x to the 3/2. Okay. And then we have this, so the first, so the h bar, so the term to the power h bar to the power 1 is integral of w11 plus 1 over 6 triple integral of w03. I just showed you how to compute w11 in the previous slide. W03 is even easier to compute. You compute them, you substitute, and you find that you have 5 over 48 z cubed, okay, and so on. I mean, you can compute the full expansion. And you can check that it satisfies the following equation. Psi second over psi equals x, basically, and which means it's the airy function equation. In fact, well, the fact that this psi satisfies, so this, if you take WGNs to be the generating function of intersection numbers, the fact that it satisfies the airy equation, I think it was already in some papers by Jul2Wed and Bertrand Eynard long time ago, but here we derive it from the topological recursion. Sorry?
Conceived, I think.
Yes, even considered.
Yeah,
yes.
That's the title of his paper, intersection numbers and the area function.
It's not the same area function.
No, but that you get an area function in the expansion? Well, maybe.
Well, Kontsevich was about matrix area function, and here it's the standard area function.
It's the classical one.
Yeah. So, but I mean, the fact that intersection numbers do satisfy this array equation is a classical result, but here we derive it from the topological recursion, and the goal is to be able to generalize that to other cases later.
How do you know about the higher terms in H
Sorry?
bar? What about the higher terms in H bar?
Well, there is the h bar square is with 1 over, as a coefficient with power, negative power of z, which I don't remember, or what. Okay,
Well, you
just replace.
Oh,
but you don't want them anymore.
Sorry?
Now you have psi additive.
Yeah, yes.
Right,
So,
take the
yes,
losses,
so when you take this ratio, psi second over psi, you have only that. There is no h bar expansion. All the h bar terms do cancel exactly, and that's what you get. Well, usually people like to write it in this form. They take y hat to be the operator h bar d over dx. And so the equation satisfied by psi is y hat square minus x applied to psi equals 0. So y hat square minus x is an operator which annihilates psi, and observe that y hat square minus x is very similar to the spectral curve you started with. So this is why people call this one the quantization of a spectral curve. So basically here, because here now you have that y hat and x don't commute, our commutator is h bar, and this, there is an operator which annihilates psi and which is somehow the quantization of a curve we started with. So in that case it is quite simple.
But how the differential equation can be changed?
Well, it can be, well, there exist now several proofs in the literature.
No, but with substitution, how it goes?
Okay, well, you know that the WGN satisfies the recursion, and basically you can prove it from the recursion.
So they're equivalent to this differential equation, right? Or, I mean,
Well, I don't know if you can say equivalent, but at least the recursion implies that. In that case, for that curve, the recursion implies that.
Because you're saying the recursion involves many C's,
Yeah.
and this is a diagonal specialization.
It can be proved through the recursion. in that
Yes,
case.
because you're working with a specialization,
Yeah.
topological recursion is more general than what
Yeah,
you're
yeah,
doing.
yeah. So in that curve. So let me show you now the example where when the TKs are not vanishing. It's very interesting. So when the TKs are not vanishing, you can do the same thing. So now let me take only T1. So y is z minus T1 over 3z cubed. So we have only one TK which is non-vanishing. You can eliminate z between x and y, and you get an algebraic equation, which is that one, y squared. So it's a polynomial equation in x and y of degree 2 in y and of degree 3 in x. Okay, it's just the elimination of z. Again, define psi as the exact same formula. Define psi by the exact same formula. And to the first few orders, what you have is, well, now, sorry, there is no dot here. The dots are in case there are more TKs. So here you have, again, this x to the 3 half plus an x to the 5 half, and so on. And here the first h bar term contains, as before, the 5 over 48z cubed, but there is also a t1 over 48z, and so on. And for the h bar square terms, you shall find here polynomials in 1 over z. Well, okay. And it satisfies, this psi is annihilated by a certain operator. Well, let me write the equation. So the operator which annihilates psi is that one, with again y hat equals h bar dx. So you see you have well, here, for instance, you have a term x minus u times y hat square, but u is something which starts with 3 over t1, plus it has an h bar square term. In fact, there is also an h bar 4, h bar 5, 6, and so on. It's a power series in h bar square, in fact. But it has all the, I mean, there are terms for all powers of h bar. It does not terminate. It's not a polynomial in h bar, it's really a series. And you can check that this annihilates psi. You can check, so just observe one thing. Now, if you send h bar to 0, when you send h bar to 0, all those other terms disappear in the limit h bar going to 0. And what you find is basically x minus u times that. And so it's factorized somehow. And you see also that in the limit h bar going to 0, 2u is 6 over t1, that cancels with that one, so this is just an x. And so observe that in the limit h bar going to 0, this factor exactly becomes that. But you see, it's factorized. There is an extra factor. So we will do the analogy with knots later. You know that John's polynomials are annihilated by a certain, there is an A polynomial associated to John's polynomial, and usually people consider the spectral curve to be only the geometric component because it's factorized. The A polynomial is factorized, and but the operator which annihilates psi somehow knows all the factors. And here we have the same kind of thing. So somehow this is like the geometric component, but this is the full thing. Okay.
So are you saying that for any spectral curve, this psi of x will satisfy some differential equation?
Yes, more or less.
H bar coefficient?
Well, more or less. That's not proved in full generality. That's been proved for many cases, case by case. I mean, we only have proofs case by case. For the moment, we don't have a full general proof, and we don't really know the conditions on the spectral curve for that to hold. Well, what I would like to say is that psi, so the same psi, the exact same definition for psi for more or less all cases. No, there will be extra terms with theta, there will be extra theta terms later, because here we have a spectral curve of genus 0. It's CB1, basically, the spectral curve. But when we have a spectral curve of higher genus, there will be extra theta terms, but basically the same psi. The same definition for psi will be the wave function, which is annihilated by an isomonodromic operator. So this is the claim. It's not been proved.
But this is, it's not a power series in H. It's really a polynomial even in H bar, this operator.
No, it's a power series in H bar.
Well, here, I can't tell because it runs off the slide. Is there?
Sorry?
And here it runs to the edge of the slide.
It's the last term, but U itself is a power series. And what I call U dot is basically the derivative with respect to that variable.
So it is a second order differential equation
Yes.
and variable x.
Yes.
these coefficients, which are some
Yes.
function of
Yes, yes, the coefficients, so it is a polynomial in X. So to all orders in H bar, it's a polynomial in X of degree 4 maximum. So the degree in X is 4. But the coefficients are power series in H bar. And the coefficients, so basically given by this U. This U is a power series in H bar, and if you write it in terms of that reduced variable, it satisfies the Parevet-1 equation. So that's how we know that U has terms to all powers of H bar, because it satisfies that equation. In fact,
so this is the definition, because there was no definition of U. So
Yeah.
U, if you simply reparameterize, then it's the
yes.
Parevet.
yes,
So
U
is this some kind of an isomodrome condition?
So, yes, it's because there is an isomodromic system behind that. And in fact, in general, when you turn on all the TKs, well, several TKs, you have, so if you turn on T1 up to TK, you have a 2K plus 1, 2 minimal model reduction of KdV. So basically, Parevet-1 is the 3-2 reduction of KdV, and in general, you get the 2K plus 1, 2 minimal model reduction of KdV. And somehow, the fact that this psi satisfies a certain, is annihilated by an isomodromic operator. By isomodromic, I mean that it's a polynomial in X here. So it has no monodromy in terms of X. I mean, this operator has no monodromy when X moves in the plane. Because otherwise, you can always say that psi will satisfy a differential equation. Just if you want to be stupid, you can just take your favorite, any definition for psi, define, I don't know, define f equals psi prime over psi, then you immediately have, well, that y hat minus f of x annihilate psi. I mean, this will be true for any function, and you don't learn anything from that. What you learn here, which is interesting, is that the f has some special property.
Well, it's polynomial.
Sorry?
It's polynomial.
No, in this example, no.
No, in your example.
Yes.
It's polynomial
Yes,
X. That's
yes.
very
So
strong.
that's a very strong statement.
Yeah.
So that's an extremely strong statement, and that's what I call isomodromic.
No,
and
that's not
whenever,
isomodromic. Wait, just a second.
yeah.
I can write down any polynomial.
Well, it means so this implies
the monodromic
that
group is constant.
okay, this implies the fact that it's polynomial implies that the Stokes matrix, the Stokes matrices when you go from one asymptotic sector to another don't depend on X. This implies that, and that's what I call.
So if you have a equation with polynomial.
Okay, we can discuss that later.
There might be monodromy.
Okay, you can discuss that later, but it's strongly related to Miwa-Jimbo formalism and everything. The fact that you have such an equation is related to the existence of a time function, of Plucker relations, of Hirota equations, and all that, and it implies that there is a Lax system and all that.
But the isomodromy is not the differential equation of second order, it's the Parevet equation. If you put some other U,
all this is very strongly related. Okay, I don't have time now. We can discuss that later, but all this is very strongly related. And so for every such equation, you will have a nonlinear equation of that type. So so in the 2k plus 1, 2, you will have basically the Gelfand-Dickey polynomial here. The case Gelfand-Dickey polynomial equals S.
May I ask?
Yeah.
So if you started with a polynomial spectral curve
Yes.
in x and y, but general polynomial,
Yeah.
so do you expect if you go through your
Yes, that's what we did more or less with Borot
That's
and
what
Berger. We get the K. In fact, if
not y squared, not this,
Yeah.
any polynomial in x and y,
yeah. Oh no, sorry.
any polynomial,
so-
but polynomial.
Okay, that's a okay. We conjecture that. It's not proved, but we conjecture it. But we have not been able to prove it for a moment. But what we have proved with Borot and Berger is basically in the case where you take x of z equals a polynomial of z and y of z equals another polynomial of z, then this will be a reduction of KP hierarchy. If you have that, then we can prove that it's a reduction of KP hierarchy. But for more general curves, for the moment, we don't have a fully general proof. We have proofs case by case.
But you expect.
But we expect that this should be true all the time.
And do you know the transform from the spectral curve to the equation?
Yes, more or less. at least we know the transform from the spectral curve to the spectral curve of the lax matrix. Well, but yes, the answer is yes, and I will give the formula a little bit later, in fact, in this talk, if I have time. What's the time? So, let me move to not polynomials. So here is a figure of 8. I don't draw it in real time before. Hyperbolic knots have a so-called apolynomial associated to them. While the apolynomial somehow is the relationship between meridian and longitude holonomies along the knot. I don't want to enter the details, but it's been, I mean, it's well tabulated in the, you can find it on websites, the apolynomials of any knots, basically. It's well tabulated, and for that knot, you have a polynomial in e to the x and e to the y, while usually people prefer to write polynomials in, usually they use the variables which are the exponential, which are the exponentials, but if I want to stick to my formalism here, and for instance having that, I need this x and this y. Okay, so this is the spectral curve, and it's, this one is a genus 1 curve. It's a torus. Okay, you can put it as in the form of a paragraph. A little bit like before, I was writing the curve in a parametric way, with x equals z squared and y equals some polynomial of z. Here you can write that e to the x is an elliptical function of z, or you can write it as a rational function of Weierstrass p of z and p prime of z. It's just a parametric way of writing the curve. With that parametric way, the fundamental second form differential is something which has a double pole on the diagonal, so it's clearly the Weierstrass function of z1 minus z2. It has a normalized double pole on the diagonal and over pole. You can add to it a constant, and here in that case you should add the second additional series over 3. It's the one which is normalized on the A cycle. Here. Okay. So this is the fundamental second Kern differential. And let's run the topological recursion. So we apply basically the same formula. We apply the same formula, again the residues, because you have, well, basically you know the Taylor, the Taylor expansion of Weierstrass function p and p prime is in the books. You can just, or sometimes it's implemented on Mathematica or anything. You can just use it and compute those residues, and you can compute the WGNs. Right? So you can compute the WGNs by this recursion. And now let's define the psi. So as I said, this is a genus 1 curve. So the formula for psi will not be exactly the same as we had before. There are extra terms. And the best way to, I could write all those extra terms, those theta functions. The formula will look horrible. But if I represent it diagrammatically, it looks very nice. So let me represent it diagrammatically. Well, first WGN. As I say, WGN, let me represent it as somehow a blob with like a genus G surface with n variables. One is WGN plus 1. So it's just a graphical representation of WGN. This genus has nothing to do with the genus of a spectral curve. It's just here, it's just an index in the WGN. Okay? Let me also represent, so since we are on the torus, there is naturally a theta function, while theta 4 is the one which vanishes where? Theta 4 is the one which vanishes at this point on the torus. So we have to pick a characteristic somehow. We take a theta function with some characteristic. And let's define the kth derivative. Let's represent the kth derivative of log of theta as a vertex with k legs, like that. And then define Jm as the sum of all connected graphs of total Euler characteristics minus m. So this is the example for J1. So J1 contains a W11, it has Euler characteristics minus 1, a W03 with a symmetry factor 1/6, it contains also W03, but where two of the legs are contracted with a vertex like that with two legs, and also a W03 where one leg is contracted with a vertex with one leg and another vertex with one leg. So this means a second derivative of log of theta, this means the first derivative of log of theta, and so on. Well, it's just a graphical representation. I could write the formula in letters. It would take several lines. It would not be easy.
But you have a formula for Jm?
Sorry?
But there is a formula for Jm not using graphs? I mean, it's a...
Yes, yes. Yes, it's completely explicit. It's a little bit like I was writing before. So
I mean, it's much more convenient.
So it's 1/6 integral of W03 from z, and here there is a base point, which I don't remember what it is, plus integral with the same base point of W11, plus, so 1/2 integral over z, and here we have bicycle integrals of W03, and here you have this log of theta second, plus I mean the last term, which is
theta second.
excuse me?
This should be theta second or theta not
So
log of theta prime prime.
Sorry?
Should be theta prime prime divided by theta not log of theta prime prime.
I'm taking the logs. No, this is that we have that.
So here there are only finitely many terms.
Sorry? No, yes, there are only 4 terms for J1. Yes, because the
No,
number
but here there are infinitely many. You have the sum Jm, and you have more and more graphs.
No, for each m you have only finitely many terms.
But you have infinitely many m and more graphs. What I'm asking is there a formula
Yes,
for this,
yes, so
for this
because I'm
whole
going
expansion?
to make, because then I'm going to put an h bar.
Yes, but I'm
m.
asking whether you have a formula for the whole expansion, not using graphs, but as a formula, not as a sum of the graphs. As a say,
well,
transintegral
I write it as a
transform.
formal series in h bar.
No, but that's fine, but I'm asking if you have a formula for the coefficients, a formula, not a sum of the graphs.
Well, I write the coefficients in terms of those integrals, yes.
But I'm asking if you have a formula for the mth coefficient. You've only given it for m equals 1 and 2.
Yes, but the formula is that one. It's the sum of
No,
all
I'm asking if you have a
graphs.
formula. A formula is not a sum of graphs. A formula in terms of letters.
Okay, I don't have a more compact formula than just the sum of all the graphs.
No,
of
so
the
you don't have.
integrals.
Okay, that was the question.
But it's a finite sum.
No, all of m goes to infinity. There are infinitely many
Yeah.
connected graphs.
Is by formula
Well, look, we have. I mean,
Feynman diagram?
no, not without diagrams.
They are not Feynman diagrams.
Well, but they're graphs.
Let's go on.
Okay. So, but, well, it's just okay. No, I don't have a more compact formula, but the claim is that this formula will work for every spectral curve in every situation. I mean, maybe for knots it will reduce to something more compact, but this formula is going to work for every spectral curve. That's what I say.
But the contraction of lines is the integration, right?
Yes, basically. Yeah.
Why does theta show up?
Sorry?
Why intuitively does theta show up?
Okay, in random matrix situation, it came naturally from what people call the sum of Filling fractions, and it appeared naturally. And then we made the guess that they should be there, but in fact, it is not. So the claim which I will make in a moment is that this psi is basically the Jones polynomial. But this is not proved. I mean, even if we would be able to prove just the very first term, it would be the volume conjecture.
You mean the asymptotic expansion?
Yes, this is the asymptotic expansion of the Jones polynomial, so that's what we claim. In fact, that's what was the claim of Digraph, Fuji, and Manabe. They checked all the first few terms, and it works perfectly.
There's no n.
Well, it's just Digraph, Fuji, and Manabe did not include the theta terms. They had to renormalize, to do a renormalization procedure, but when we include the theta terms, it works perfectly to first two orders. This is exactly the formula which Don was writing yesterday. And up to order h bar to the cube or something like that. It works perfectly. But this is a conjecture. Even if we would be able to prove just the very first term, even that one is the volume conjecture. So, and we cannot prove it apart from that very precise knot. But the claim is that it works for every knot. So for instance, for a figure of 8 knots, you can compute J0, J1, J2 explicitly with that formula, and it works. So basically, these are in digraph regime analysis paper.
Can I ask something? So,
What is sigma and what is W? Could you give
Well, it's so x, so W is just cosh x and sigma is that.
okay. All right, now I will ask. So the A polynomial of a knot in general has many components.
Yes.
Definitely at the abelian mode.
Yeah.
So if your method is to start from the A polynomial curve
Yeah.
and reduce the asymptotic of the Howard-Jones or cosine, that sees all components.
Yes.
So how do you know?
It's
How does this formula,
okay.
maybe with the thetas and whatever's, knows about the other components?
I
in
don't
particular
really-
about the abelian.
I don't really know, but that's why I showed the previous example with the Pan-V1 example. We start with the geometric component. Just starting with the geometric component, applying the topological recursion, we get a psi. And when we compute the equation satisfied by the psi, we get all the components, not only the geometric
Yeah,
component.
but here the A hat that annihilates it does not have the abelian component.
I don't know, in fact. The answer here is I don't know.
So that's probably because you have the full state. You have the
Yes.
full Chern-Simons state and not just the part
Yes,
that corresponds
probably.
to the geometrical.
So you see here, I start by defining. So you see here, I start by defining psi, and then I see what equation it obeys. I don't know in advance. I don't start from the equation.
Oh.
So
I guess you were presenting the full solution space. I take it back what I just said.
yes,
You're presenting the full solution space to the recursions.
yeah,
And the Jones polynomial is one in there, right?
yeah. So, but it is a
No,
conjecture.
It's not. It's missing. The Jones satisfies an homogeneous equation or an equation of 1 degree higher than this
Yeah.
A hat. And this is a component. This A hat is a quantization of a component of the A
Yeah.
polynomial corresponding.
I
to-
don't say what a hat
No,
is
no,
here.
hold on. Is A hat degree 3 or degree 2?
In
This
fact,
A
for
hat.
that case, I don't know.
2 or 3? It matters.
I've not
Yeah,
computed it for that case.
The answer to that is, I think I agree with you to the conditions that have to be.
Ah, okay.
Okay.
So it's
Well,
degree 2.
Okay, maybe Gaetan has computed it for that case. at least the first
When you
two
take
terms, I don't know.
asymptotics, you've thrown out the abelian component. It's very hard to.
Okay. Okay, but I just wanted to show you the previous example where you see we started from one component and we get two in the end. So, well, here I don't know what it's going to be, but the claim is that this should be the asymptotic expansion of Jones polynomials. Okay, and it works well. So we checked it explicitly up to m equals 3. Okay, I'm not going to have much time. In fact, I could more or less stop here. But I just want to say a few words about the general definition of topological recursion. So the general definition of topological recursion, you have to start with a spectral curve. And the spectral curve is the data of a Riemann surface on which are defined two analytical functions x and y, and also a W02, which is this form which has a double pole on the diagonal and no pole. And there is something which is important on the spectral curve. These are the branch points. The branch points are the points where dx vanishes, so basically where the tangent is vertical. Well, here I'm presenting only the case where we have only regular branch points, so basically where the curve looks like a square root. But in fact, the topological recursion has been generalized to even higher order branch points, but it's just I don't want to write it here. So in case we have a regular branch point, there is a local Galois involution. So I mean, the local Galois group is Z2, and there is a Galois involution which I call sigma A. Sorry, SA here. Okay. Then we define W01 to be just y dx. Well, in fact, since we are going to use because the recursion works only by computing residues, in fact, all what we need is not really a function y, but it's just a germ, a formal. So basically, in fact, sigma does not really need to be a surface. It can only be some formal neighborhoods, and y needs only to be a formal analytical germ in that formal neighborhood. We don't need more to run the recursion. So the recursion can be run even if you have just formal series. And it gives actual analytical functions. So W02 is a symmetric two-form with double pole on the diagonal. And then you define the WGN by the recursion which I wrote here, and which is more conveniently represented diagrammatically. So this is the definition. The reason why this definition was introduced is because it computes the asymptotic expansion in matrix models. And in fact, in the beginning, when I introduced that definition, I thought it would compute only the, I thought it would be only for matrix models. I didn't imagine it would apply to something else. But people started to realize it applies to many other things like topological strings, and, well, not theory, many other things which I just didn't imagine before, but it's the same recursion in all cases. There is no parameter in that recursion. It's a universal relation. What is non-universal is the choice of the spectral curve. So somehow, what is problem dependent is the choice of the spectral curve, but after that, the recursion itself is curve independent somehow.
So the degree of y is not somehow fixed?
Sorry?
The degree of y is not
totally arbitrary, and y does not even need to be algebraic. It can be real anything. So it's very convenient to represent it diagrammatically here, well, either with punctures as Riemann surfaces with punctures or Riemann surfaces with boundaries. It's just a graphical representation. It does not really mean anything. It does not mean you are really computing numbers of Riemann surfaces or worldsheets or whatever, but it's convenient to have this picture in mind. But it's just a picture. It's nothing more for the moment. It is not known whether there is really such a representation. It is not known whether this picture really means something geometric. And it's
like a signal.
Yes, it would be really nice. So somehow, well, for instance, Gromov-Witten theory of toric-Calabi of free folds does satisfy this recursion relation, where when the spectral curve is chosen to be the mirror. So it does satisfy that. We have a proof. It's a technical proof. But the proof does not rely on such a picture. And if such a picture would have a meaning in topological strings, it would mean that there is a canonical way to cut worldsheets like that, removing not a pair of points. It's not really a pair of points which you remove. We call it the short with Rampa, because it's a pair of points, but where you have somehow removed the legs, because somehow it's only one boundary here which is pinched. It's not two boundaries. It's not a pair of points. So
you mean Gromov-Witten theory of local Calabi also?
Yes, of toric. I mean, it's been proved in that case. Maybe it works in other cases, but in that case it's been proved. But the proof is technical. I mean, it does not use that picture. So, yeah. Well, also, yes, in my definition of WGN, the definition works only with n strictly positive. And somehow I never define WG0. WG0 very often we call it FG, and it can be obtained when you know WG1. You contract it with phi, which is the antiderivative of y dx. Take all residues at all branch points, divide by 2 minus 2g, that gives FG. There is also a definition for F0 and F1, because this is only for g larger than 2 because of this denominator, but I don't want to write them. So we have a definition, and it satisfies plenty of properties. Well, one of the important properties, the very first property in that definition is, you see, Z1 seems to play a special role in this definition. So the leg number 1 seems to play a special role. The definition is not symmetric in all the ZIs. But the result of this computation is always symmetric. You can prove it by recursion. So you always get something symmetric, although the definition is not symmetric. It's a little bit miraculous, but...
But you have a symmetric formula, don't you?
Well, no, as I say, the definition does not seem to be a symmetric
He's
form.
asking if you have another formula, not this one, which is symmetric.
Manifestly symmetric formula.
I think they don't.
Well, no, if you symmetrize, you can always symmetrize that formula and get something symmetric. No, but none of the definition is not symmetric. Okay. Yeah, so one important property is that the FGs are, well, symplectic invariants. I don't want to explain exactly what I mean, but for instance, one of the properties is that if you exchange x and y, you see the branch points will change drastically. instead of computing residues at the vertical branch points, you will compute residues at the points where the tangent is horizontal. So it looks totally different. The number of branch points is not even the same. It looks extremely different, but the FGs are the same. So it's a very miraculous property. So I don't want to go further. There is also modularity properties. If the spectral curve, no, I'm out of time now. Sorry. I should tell
You still have at least 5 minutes.
Okay.
No, but here's other things. Please go on.
Okay. Well, there is modularity properties. In the case where the curve has, let's say, genus, some genus, you don't see the modularity property for genus 0 curves, but for higher genus curves, the modularity property is with respect to the SP2G of the group. So it's not the same modularity properties which Don was talking about yesterday, but still it's intriguing, the fact that, well, could there be a relationship between the two modularity properties? Well, for the moment it's not known, but at least those FGs are almost modular forms with respect to that SP2G of Z. Well, this integrability is indeed what we said. So basically, starting from any spectral curve, this psi will always satisfy an isomondromic equation, an isomondromic system. This is a conjecture, as I said. It's been proved case by case for many cases already, and it's believed that it should hold at least for every algebraic spectral curves, or maybe even more general, but it's not proved.
What do you mean by 1 plus non-perturbative?
So it's those theta terms. Well, it's those theta terms. I don't want to write them. But the claim is that this is the tau function of some isomondromic system. So the claim is that this quantity is the tau function of some isomondromic system, and it satisfies some high-rota relations, some precurrent relations. There is a lax matrix and all that. Well, another very nice property is that the topological recursion commutes with taking limits, like blow-ups or resolutions. I mean, it commutes with taking limits. It's really, it's a very useful property. I mean, people who did quantum gravity in the 90s, for instance, they used to start from matrix model and define what they called double scaling limit. And the double scaling limit is very highly non-trivial. It consists in an infinite resummation of graphs and all that. And it turns out that in the topological recursion language, it is somehow trivial. It goes through. I mean, you just, in some sense, well, I put quotation marks because you have to do some rescaling, but basically, if you have a family of spectral curves, then the limit of the FGs is the FG of the limiting spectral curve, somehow. Well, quotation marks, because there are some factors which I ignore here. Well, they have many other properties, like there are some Seiberg-Witten-like relations which are related to form cycle dualities. There is Giventhal formalism. It's very strongly related to mirror symmetry. Also, it extends to non-commutative spectral curves and all that, but I don't want to enter the details. So I'm almost, well, okay, maybe I will go to, I wanted to mention just one thing. When I said that this picture has no geometric meaning, that's not totally true. There is a way to cook up a certain moduli space, a certain moduli space of what I will call colored Riemann surfaces. There is a way to cook up a certain cohomology class on that space, such that double Gn is indeed the integral over mgn of that thing. So there is a way to make this picture, this blob picture, to give a meaning to it. And it's related to Giventhal formalism.
And this is symmetric.
This is not symmetric.
This is now symmetric.
And not recursive.
And not
Just
recursive.
one form.
And not recursive. But somehow this is a little bit like ELSV formula. It's not so easy to use and compute, in fact. Well, no, the important fact is that this cohomology class is in fact very simple. The formula for this cohomology class is just made of kappa manifold classes, and it's made out of a spectral curve. And the way to compute that cohomology class out of a spectral curve is extremely simple. It's only Laplace transform. So
and is this a sort of discrete moduli space?
Yes, it's more or less like when you have localization. For instance, well, basically I use that formula to prove that Gromov-Witten theory of toric Calabi-Yau spaces do satisfy the topological recursion. That's basically how I proceed, because when you have toric symmetry, you can reduce the moduli space only to the toric invariant part, and the toric invariant part is basically made of such surfaces. I mean, these are the toric invariant surfaces, and this is more or less what the proof uses. So it's a kind of combinatorial moduli space. So that's why it's not so satisfactory, this formula. Somehow you cook up an ad hoc modular space such that you have that formula, but this ad hoc modular space is not really what you would expect. I mean, it's not a really three-dimensional modular space of really three-dimensionality or something. So it's a little bit disappointing from this point of view, but it works. And the nice thing is that this cohomology class is extremely easy to compute. You just take ydx, the form ydx, multiplied by e to the minus ux, integrate on some path which I will not, which I call a steepest descent path, and that defines the Laplace transform of this one form ydx. And when you take this Laplace transform and take the log, expand it into powers of u at large u, so compute the Laplace transform at large u, expand in powers of u, you get some coefficient t hat case, and then the class here is just the exponential of those sum of t hat case kappa k. And this is just the class you put here. The b hats are more or less the same thing with Laplace transform of W02. When you apply that to some curves, for instance, if you take your curve to be the Lambert function, so if you take y to be the Lambert function, you apply that, you get the combination you get here, while the tk's you get are some Bernoulli numbers. The combination of Bernoulli numbers is exactly the Hodge class, and basically you recover ELC formula to do that in a couple of lines computation, which, I mean, the most difficult computation is just compute the Laplace transform of Lambert function. So, another example is now take y equals sine 2 pi z over 4 pi, where x equals z squared. So this curve is not at all algebraic. Someone asked about algebraic curves. This curve is not at all algebraic. Compute the Laplace transform. It's extremely easy. You get e to the minus pi square over u. So which means that the tk's, which correspond to the large U expansion of that, there is only t1, t hat 1, and which is pi square. So the class is just e to the pi square kappa 1, which is the Weil-Petersson form. And so just this theorem shows you that the double GNs are the Weil-Petersson volumes. So you see the most difficult part of the computation was this Laplace transform, which is totally trivial. And Charles here could do that probably. Student could do that. And it's totally trivial computation. And what you have proved basically, while saying that the Weil-Petersson are the double GNs which satisfy the topological recursion, shows you that Weil-Petersson volumes obey Mirza-Randi's recursion. And it's a very easy proof, I mean, using that theorem. Okay. Well, I think I should stop here. Okay, thank you for attention.
Thanks. Questions?
Yeah, you promised in the middle of the talk that you would give a construction of the Ping-Way.
Yeah.
I have a question.
Well, okay, well, just a few words. So again, I define, so for an arbitrary curve, I define again the JNs with the same formula. So here are the first few terms. So I define psi with that formula. So I take all those JNs. So it's a systematic construction for every spectral curve. So it contains the usual terms plus the theta terms. Okay, and what I do for Hitchin system, is basically you see for every x on the base, it has several preimages. That's what I call the pi of x. They are the pre-images. So you take 2 points, x and x prime, take their pre-images, that makes a matrix of rank R. Okay? Now take phi to be deep psi times psi minus 1, then the claim is that this is a Higgs field. So, and somehow that it's something well defined on the base. Okay, that's the claim. Basically, Moulassé and Dimitrescu have proved it last year for rank 2 systems. We have a proof for rank 2 system, and we are working with Vincent Bouchard on the proof for rank R. It's not published yet, but basically we have a proof, but it's not just generalizing Dimitrescu and Moulassé. It's not been published yet, but really soon, I hope.
More questions?
Yes, somewhere in the middle you mentioned connection to KGV,
Yeah.
obviously the Schrödinger equation.
Yeah.
Could you write the potential for that Schrödinger equation?
The potential for the Schrödinger equation. Yes, but I wrote it. It was written on my slide. Well, I can show it again.
So, but you said that it is a monodromy-free equation.
Yeah.
Yes, but I can't imagine a monodromy-free equation with polynomial coefficient, except maybe with the constant
Well, that's-
equation.
yeah.
Because,
I don't think you-
because one solution can be polynomial, but the second solution will always have monodromy.
Yes. No. No. Sorry. It does not mean psi has no monodromy. What I call isommonodromic system does not mean psi has no monodromy. It means the monodromies are constant.
A constant, sure.
What is called?
The monodromy.
The monodromies don't depend on
The
x.
usual meaning of isomonodromy. It doesn't change.
And the time-dependent potential in the Schrödinger equation, and the monodromies do not depend on the time of the
Yeah.
potential.
Yeah, the monodromies are constant. That's what is meant by isommonodromic system.
Could you go? I mean, I didn't understand the connection at all. When you wrote down the A polynomial for the 4-1 curve, and then suddenly you had an equation with the Weierstrass P functions, I don't know at all what the connection, and then you, on the next page, you had formulas that there were no more.
But
The-
what? Yeah.
You showed us three formulas. You started with the A
Yeah.
polynomial of 4-1,
Yeah.
and then you wrote something with an integral with Weierstrass P functions.
Yeah.
That was, or just the Weierstrass P functions for W02.
Yeah.
And then, if W02 is the P function, the higher one should also be elliptic function, but then you just showed us on the next slide some polynomial. Can you go back? I didn't understand that at all.
Yeah, well,
You had a
the
W02
WGNs are elliptic functions.
Sorry?
The WGNs are elliptic functions, so you can write them in principle in terms
But you
of
wrote
Weierstrass
looked like just
functions.
polynomials on the next page. It was very strange. Yeah, here.
No.
Where are the here in that, on that page?
Okay, because the WGNs are polynomials. No, in fact, you have a sigma to the 3of, so it's not really polynomial.
But I don't see any modular forms and elliptic functions. I just see polynomials. 2w minus 3 times 2w plus 1.
Well, first,
On the previous page, you had
first, those coefficients for the expansion of the Jones polynomials were known long before we did our work.
I'm asking about that. I'm asking, in the previous slide, there's an elliptic function. Where did it go?
Yeah. Well, you use the elliptic function to compute residues, so it just gives numbers. But the WGNs are indeed elliptic functions. But when you integrate them, somehow you integrate them in a way which is symmetric in
No, but you're integrating in the elliptic variables, so you should still be left with quasi-modular forms.
Isn't X an elliptic function?
Sorry?
In a sense, what can you integrate it from?
Can you go back
Z
one,
plus
please?
iota of 0, you actually divide the curve by an
Yeah,
integration
yeah.
which makes it genus 0.
I didn't write all the details, but
No, here.
So here you
So
have,
here, W02
Yeah.
is given explicitly with an
Yeah.
elliptic function.
Yeah.
So
okay.
even if you integrate that, you'll
Okay.
still be left with quasi-modular
Okay,
forms.
it's all contained in that small detail here. When you integrate along a certain chain. Okay, and the chain is somehow is symmetric under the elliptic involution. So what you get is symmetrized under the elliptic involution. Basically, yes, in the end you get only polynomials. With
But they should still depend on the elliptic, on the parameter, on tau. Where is the quasi-modular
yes, but
forms?
for that case, tau is a very specific value. I don't know. I mean, it's completely fixed tau.
Oh, I see. That Weierstrass P function was for a particular elliptic
Yeah,
curve.
yes.
For that elliptic
It's called
curve.
the spectral
I see.
curve.
Okay.
Yeah. So it's
So
very
it's
specific
not
value of tau.
okay. I see. So there's special values.
And
Okay.
somehow
Thank you. That was the question.
Yeah.
I didn't see where the where
the
they
value
go.
of tau is contained somehow in those coefficients 10, 17, and something like that. And the value of tau is hidden in there. And for another tau, you would get different numbers.
So if you go back, if you don't take 4-1, but take the same form with P, with the Weierstrass P function, you could do that with the parameter
Yeah.
tau. And then what would that be counting? Does that have some meaning, that particular? So if you did that topological recursion with the same W you showed us,
Yeah.
but P is now the Weierstrass P function for any elliptic curve, then you'll get a sequence of higher WGN.
Yeah.
And you can integrate, you can do all of this. Do you know what that, does that have any meaning? It looks
Well,
very beautiful.
Somehow I showed you that for every spectral curve you can cook up a certain moduli space, and somehow this is the counting function for that moduli space.
No,
but it
but
is an ad hoc construction.
sometimes it's an interesting problem.
Yeah,
Asking
yes,
if you
exactly.
know, you don't
So
know.
the full general answer to your question is not no.
Okay.
So in fact, this is basically Moulasset always starts his talk by saying we have a nice definition now. Let's understand what it computes.
I have a question. So you said that starting from any spectral curve, you can construct family of tau functions.
Yeah.
Alright?
Well, that's
Yeah,
condivision.
reproduce at least any more or less known families of tau functions for many systems. I wonder, normally tau functions, they decide some kind of quadratic recurrence relation.
This is here.
So, yes, where you can just iterate them and just reproduce high terms, high tau function. Is it always the case in your case, or are there any
Well,
such?
as I say, we miss a general proof, but case by case we can prove that yes.
Okay.
But yes, the claim is that this should always be the case. But for the moment, we don't have a fully general proof. And in fact, one consequence of all that is that it claims that the John's polynomials is in some way a tau function. The John's polynomial is a tau function. That's what you can deduce from that expansion.
No more questions? Let's take the speaker again.